If a straight line be cut at random, 4 times the rectangle contained by the hole and one of the segments, together with the square on the remaining segment, is equal to the square described on the hole, and the aforesaid segment as on one straight line. So starting with line AB, we're going to cut it at random at C, and draw BD in line with AB equal to CB. What we want to show is that 4 times AB times BC plus AC squared will be equal to AD squared. We will do this by drawing a square, AEFD. We can connect ED, and then, in the usual way, from C and B, we draw lines CH and BL parallel to DF, and through K and Q, we draw MN and OP parallel to AD. The first thing we need to show is that these 4 squares are equal. We do this by noting that CB is equal to GK because it's a parallelogram. Similarly, BD is equal to KN because it's a parallelogram. And so CB being equal to BD, GK is equal to KN. And for the same reason, QR and RP are also equal to these values. Now we know that parallelograms CK and BN are equal because they are on equal bases and CB is in line with BD. We also know that CK and KP are equal because they are complements of the parallelogram CP. And parallelogram GR is equal to parallelogram KP because they are on equal bases and in line with each other. Therefore, all of these parallelograms are equal to each other. And, therefore, CP is 4 times CK. The next thing we need to show is that AG and MQ and QL and RF are all equal to each other. Now because these are all parallelograms, we know that AC is equal to MG, which is equal to OQ. Same for PF, RL, QH, these are equal to each other. And since CG and GQ are equal, parallelogram AG and MQ are both on equal bases, and AM is in line with MO. Therefore, these two parallelograms are equal to each other. For the same reason, parallelogram RF and QL are equal to each other. And since MQ and QL are complements of the parallelogram ML, we know that they are equal to each other. Therefore, all 4 of these parallelograms are equal to each other. Now, since these 4 squares are equal to each other, we can add separately one of each to each of the 4 parallelograms we just proved were equal to each other. And we therefore find that the entire nomen of AD, being the square on AD minus the square OH, is equal to 4 times AK. Now AK is equal to AB times BC, because BK is equal to BC. Therefore, if we multiply this by 4, we get the big nomen, and if we add the square on AC, which is OH, to this, we then have the entire square on AD. Therefore, 4 times AB times BC plus AC squared is equal to AD squared. It should be noted that in this proposition and in several previous, we've only been dealing with squares. AEFD is a square, and all those 4 little squares were squares. But we've proved previously, in the first book of Euclid's Elements, that the area of parallelograms are invariant to skewing. So if we held AD fixed and we moved EF around to get different parallelograms, we would arrive at the exact same results.